Hey statistics class, this is a video I have prepared for all of you. I've created several slides, as you can see here, for all of Chapter 7, and we're just going to go through all of these slides so you can learn about what is the normal probability distribution. This is what all Chapter 7 is about, normal probability. So let's go ahead and get started on it. Bring this up. There we go. Okay, so chapter 7. Let's look at what section 1 is about. Okay, in section 1, we're going to see properties of the normal distribution. And these are some of the objectives. We're going to maybe skip over a couple of them and just hit some highlights of this section. So let's go ahead and get started on it too. We have done histograms and relative frequency histograms before in class. And this is what they say about normal curves. Relative frequency histograms that have symmetric and a bell shape are said to have the shape of a normal curve. So you'll hear that a lot. Normal distribution, normal curve. All right, it is said that if a continuous random variable is normally distributed or has a normal probability distribution, then a relative frequency histogram of a random variable has the shape of a normal curve, which is bell-shaped and symmetric. So here we have a normal distributed random variable or a normal probability distribution shown by this graph right here. This peak right here is going to be our mean of our data given to us. And then from our data given to us, we can find the standard deviation of that data. And this inflection point right here and over here, it always happens one standard deviation away from the mean. So, or our first standard deviation away from the mean on both sides of the curve. And if you've had me in calculus before or are in calculus right now, you should know what inflection point means. It's not that important at the moment in our statistics class, but just to let everybody know, an inflection point happens when we have a graph of our function or just a graph of an equation, and at some point right here it changes concavity. So the point in which the concavity changes on a graph is called an inflection point. So this changes from being concave up to concave down at this point right here, called the inflection point. And same on this side right here. Okay, so let's move on to the next thing. Now, depending upon your data that you are given, your peak of your curve, which is always the mean of your given data, can change from one place to another depending on what the mean of your data is. And here it shows that, okay, a curve is centered around 0 with standard deviations of 1 and -1 on either side of that mean. Well, you can have the same exact curve, but it can be shifted over because it has a different set of data where the mean is centered around 3 rather than 0. And then that causes, whenever you have this case right here, you and your standard deviation is the same amount, you just have the same bell curve shape, but just centered around a different mean, but the same standard deviations on either side of the bell curve or across the mean. All right, and then let's look at this information down here that I have, this picture. We have two sets of data, both centered around 0 as the mean, except we have a different standard deviation on each. The one that's graphed in kind of this pink or reddish color here has a standard deviation of 1. And then the one that's in blue has a standard deviation of 2. And what happens whenever you have a smaller standard deviation is you have what's called a narrow bell curve. And then whenever you have a greater standard deviation, you have you have a wider bell curve. So this is what happens in those two cases. So to kind of overview here, it says properties of the normal density curve are these right here. It says it is symmetric about the mean, or known as denoted as this Greek symbol called mu. And because the mean equals the median and that equals the mode, they're all the same, the curve has a single peak and the highest point occurs at x, which equals our mean. It has inflection points at 1 standard deviation away from the mean, both plus and minus. This was supposed to be a plus sign right here. And then the area under the curve is 1, just like all the probabilities that we have dealt with so far. Any probability distribution we have looked at, all of our probabilities add up to 1. And the same thing goes with the probability under this curve, the area under the curve. It is always equal to 1. The area under the curve to the right of our mean is equal to the area under the curve to the left of the mean, which is 1/2, which makes sense. If our data is centered around the mean, then the peak in which the mean happens is to the left, you're going to have 1/2 of your data, and then to the right, you're going to have the other half of the data. Now this next property, number 6 here, I'll show you the graph on the next page and you'll see what I mean by it. But as x increases without bound, meaning it gets larger and larger, the graph approaches but never reaches the horizontal axis. So let's take a look at that here. So as it moves this direction or moves this direction, this line will never cross the x-axis. It just gets closer and closer to 0 or y equals 0 on your graph there. I already stated the other half of 6. Whoops. As we looked at the graph. But as the x decreases without bound, meaning it gets more and more negative, the graph approaches but never reaches the horizontal axis again. All right, and then we've looked at something called the empirical rule before, but it is said that approximately 68% of the area under the normal curve is between 1 standard deviation away from the mean, so x equals mean minus 1 standard deviation or plus 1 standard deviation. And then approximately 95% of the area is between 2 standard deviations, meaning x is between the mean minus 2 times the standard deviation or 2 plus the standard deviation. And then lastly, approximately 99.7% of the area is between 3 standard deviations away from the mean. So your x value is equal to the mean minus 3 times the standard deviation or plus 3 times the standard deviation. Okay, let's take a look at that graph again just so you can get a better idea of what this empirical rule is referring to. So here, 1 standard deviation within the mean happens between these values right here given to us. So 34% here, 34% here. That makes up 68%. That's within 1 standard deviation. Okay, 95% of your data centered around your mean is within 2 standard deviations of the mean. Okay, and then 99.7% happens within 3 standard deviations of the mean. So there you go. That is how we look at standard deviations and the mean and things like that against data that is normally distributed. Now, one more thing of information that I'm going to tell you before we go to an example is this right here. It says area under a normal curve. Suppose that a random variable x is normally distributed with mean and standard deviation. The area under the normal curve for any interval of values of the random variable x represents either the proportion of the population within the characteristic described by the interval of values, or the probability that the randomly selected individual from the population will have the characteristic described by the interval of values. So that is how you interpret or explain the role of the area under the normal curve. Okay, so we'll have some examples that will ask for you to explain or give reasons behind the area under the curve or an interpretation. So let's take a look at a little example. Now, some of my examples I have answers already copied and pasted into the slide just because it was easier for me to do that rather than draw things out or work things out with you. But some I do work out with you on this video. So just follow along and take good notes and everything so you can better understand it whenever you come to the assignments that I have assigned for you. Okay, so for this example, it says the data on the next slide represents the height in inches of a random sample of 52-year-old males. We are asked to draw a histogram of the data using a lower class limit of the first class equal to 31.5 and the class width of 1. So when we do that, I am not going to ask you to draw histograms with this much information given to you because there's a lot of data on the next slide. I will end up showing you how in a later a slide or lesson in this chapter on how to use your graphing calculator to draw histograms using or with a set of data. And I'll also show you another type of graph too, called the normal density function. But anyway, let's look at this example on the next slide. I'm going to ask you to draw a histogram, and then we're going to answer, do you think that the variable height of a 2-year-old male is normally distributed? And we're going to answer that just by looking and seeing if the histogram, the data, represents a normal bell curve. So here's the data that you would want to plug into your calculator at some point. I'll show you an example similar to this later, like I said. But this is the data that would be outputted to you on your graph. Here is a histogram showing the heights of 2-year-old males in inches, and with the width of 1 and starting at 31.5, like it asked us to do. Okay, so taking a look at this right here, this histogram looks fairly similar to a bell curve. As you can see, whenever I go to the next slide here, this is just drawn the width this is the same graph right here, but drawn with a normal bell curve over the data, as you can see. So what I would say is that yes, let's answer that question properly. That yes, that the height of 2-year-old males is normally distributed. Okay, so there's the answer to those two questions right there. Got a histogram, and answer for that one, is it normally distributed? And the answer is yes, it is, because it fits the criteria and looks like a bell curve. Okay, so let's look at another example. In this example, it just says, suppose a random variable is normally distributed. That information is given to you. It is normally distributed, with a mean of 400 and a standard deviation of 100. Part A, draw a normal curve with the parameters labeled. And then part B, shade the region under the normal curve that represents the probability of observing a value of random variables that is less than 600. Part C, suppose the area under the normal curve below 600 is 0.9772. Provide two interpretations of this area. Okay, so this next slide, I already have drawn in, or copied and pasted in, a graph of what you would draw, of how you would draw a normal distributed curve with the mean of 400 and a standard deviation of 100. So right here at the peak is 400, which is our mean, and then you draw every, or put on your x-axis 100. So this direction, just make sure it looks fairly even. So this way, go all the way to 0, and this direction, go out to 800. And you have a fairly symmetrical bell curve here in that case, and whenever you draw it like that. Okay, now on part B, we're asked to, let's see, go back to it. Shade the region under the normal curve that represents the probability of observing a value of random variables that is less than 600. Okay, so here at 600, if we shade in this whole region here, that is everything that is less than 600, or to the left of 600 is less than. And that's all you have to do. You're just asked to shade in that region. Now, on part C, we're asked to interpret the area under the normal curve below 600 if we know the probability is 0.9772. So provide two interpretations of this area that is shaded here. And the way I would interpret this is this right here. I would say the proportion of observations of the random variable that will be below 600 is 0.9772. So let me write that out for you. Where's my pen? There it is. So the proportion of observations of the random variable that will be, not that is, that will be below bellow. Excuse my spelling. Below 600 is 0.9772. And that's one of the interpretations. The other interpretation is this right here. I'm going to write it out. Probability that a value of this random variable will be below 600 is 0.9772. Zero 0.9772. Okay, so there are my two interpretations of the area that is given to us for the shaded region of everything left to 600. Okay. All right, another example. Let's we're pretty much asked to do the same thing, but with some different given information. So it says the graduate recorded exam, or the GRE, which many of you will take in the near future, is a test required for admissions to many U.S. graduate schools. Students score on the quantitative portion of the GRE follow a normal distribution with mean 150 and standard deviation 8.8. In addition to other qualifications, a score of at least 152 is required for admissions to particular graduate schools. Draw, first part A, it says draw a normal curve with parameters labeled. So we are going to, since this is our mean up here, this 150, our curve, the peak of it would be right there at 150. And then each of our standard deviations that we're going to label will be point or 8.8 away from the mean. And then just keep going out away from the center there. But it should end up looking like this right here. Okay, so it says in part B to shade the region under the normal curve that represents test takers who score above 152. So 152, I'm going to say, since this is 150, it's pretty close to the mean. 152 will happen right about that line right there. And everything to the right of that curve is the shaded region, which represents the scores that happened above 152. Okay, so there's part B. And now in part C, it is asking us again to provide two interpretations of this area. Okay, it says suppose the area under the normal curve above 152 is 0.4090. So again, just let me write it out here. It says the portion or proportion of students who score above 152 is 0.4090. So that's one interpretation, or you can say this here. The probability that a randomly selected student will score above 152 is 0.4090. And there are our two interpretations of all the scores above 152. Well, that's all I have for you on section 1. Next part is going to be section 2. So I will start here in the next video. I'll see you then.